seem to lower energies, right? So I got a demonstration for this. Okay. Okay. So we got a cloud. I want to make a cloud. This is the cloud in the bottle demonstration, yeah? So what's in a cloud?
Water.
Yeah, there's water vapor. So I'm going to get water vapor in here. Okay. No, just a cloud, like, you know, in the sky. Like Oregon, right? Okay. Now, don't we have to mix the water with the air? Yeah, so I'm doing that, right? I'm raising the humidity of this air to 100%, right? Okay. And then all we have to do is drop the temperature of this mixture, and it should condense, right? Because the ability of air to hold water in it decreases as the temperature goes down. Okay? And so if I just drop the temperature suddenly, and what I'll do is I'll allow it to expand, right? Now I will not suck on the bottle. What I will do though is I will reduce the pressure in my mouth lower than atmospheric, right? And that will cause the air which is in here, which is at atmospheric pressure, to expand into my mouth. Okay? Yes? A brave and bold maneuver. That will drop the pressure very quickly, and a cloud will form. Are we ready for this? Okay, here we go. I'm doing it in the light so you'll see very clearly a big foggy cloud appear in the bottle. Are you ready for this? Huh? Pretty cool, isn't it? I'll do it again so if you didn't see it the first time. Huh? Do you see that? Oh, I forgot one more ingredient. There's one more ingredient. And here's the problem, right? Is that the air really, really wants to form droplets, but there's no, what you need, since I shook it like that, I took all the crap out of the air. You need crap in the air. Okay, so what I'm going to do is I'm going to put little particles of soot in there. There we go. Let's let all the sulfury stuff burn off. And let's go. There we go. There should be enough crap in there now. For all those little droplets that want to form, it's called a nucleation site, and they can form on those little things there. Are we ready for this? Thank you very much. Woo! So this is, and then this is how clouds form. Do we know this? Do we know this? We don't know this. Water vapor. Whew, a little bit dizzy here. Okay, water vapor, okay, evaporates and the air has some moisture in it. As the air goes up, doesn't the air pressure drop? Yes. And as the air goes up, the air pressure drops. As it drops, the air is allowed to expand. As it expands, it cools. And so the air up on top of Mount Hood is colder than the air down here. Yes? Yes. So when it's raining and cold here, it's snowing up there, correct? And that's a happy thing, right? Okay. So, okay. So what this air with moisture in it rises, it expands, it cools, and at some magical temperature called the dew point, okay? It condenses if there's crap in the air, and there's always enough crap in this air, right? Okay, and it condenses and it makes clouds. So you can predict, by knowing the humidity down here and the temperature down here, you can do this whole thing, right? And you can predict where the clouds are going to form. And that's a certain type of cloud formation, and then of course clouds can move around and change, and I'm not really very knowledgeable about it, but I do know that, right? So you can do these cute little graphs, especially in the Midwest where there's not mountains and things like that to throw a wrench in the work, where you can predict the height of the clouds. And that's what height they're at. Okay. And then this is an adiabatic compression, right? How do I know that's a compression? It's a curvy line. How do I know it's a compression? It's going from more volume to less volume, correct? Okay. So here's an adiabatic compression. And with compressions, if it's adiabatic, means that Q is 0. That's what adiabatic means, right? Work is done on the gas. No heat flows in, and so basically if the work is negative, then the change in internal energy has to be positive, right? Now the wall of the room we're in is moving in on us, and as the ball bounces off a wall moving toward us, this is what I do in soccer as a defender. This was my main move, right? The ball comes to me, what do? I kick it down to the other end of the field, right? I move my foot toward the ball, it comes off my foot with more kinetic energy, off it goes. Right? Oftentimes that's a good thing, right? They send it your way, you send it right back. Okay. Okay, so if it bounces off something moving toward it, it comes off with a greater speed, therefore greater kinetic energy, therefore greater temperature, and the temperature increases. Okay, examples of this: bike pump. You ever touched your bike pump? The part where the air comes out gets hot, doesn't it? How about a compressor? Does anybody have an air compressor in their house? The air compressor's got little heat cooling fins on it, like your lawnmower has, doesn't it? Is that the part where the compression happens and where it gets really hot? Yeah, if you can get it hot pumping up a tire, imagine what a 1 horsepower motor can do running for like 30 minutes, right? It can get pretty hot. A diesel engine. We already talked about this, right? In the diesel engines have compression ratios like 40 to 1, right? I think cars are like on the order of like 20 to 1 or something like that. I could be all wrong on this, right? Diesels have a really, really high compression ratio. So what they do is they just take air, not air and fuel, but just air, and they compress that air until it's fiery hot. Then at that moment when it's fiery hot and when the piston's ready to move down, okay, piston goes, right, it's ready to move down, then you inject the diesel in there and it goes kaboom! Right, the diesel goes, hey, there's enough kinetic energy here for me to, I can just combine with that oxygen just like that, right? It goes kaboom, and without spark plugs, all it needs is just proper timed, the fuel injection has to be properly timed, right? Okay, that is the timing, right? And so the diesel goes kaboom and it goes out, right? And then it's got to get rid of, it's got another stroke where it gets rid of the combustion gases, just like we did with the physics cannon, remember that? We rolled it back and forth to get the bad stuff out, right? So it's got to have another stroke in there where it gets rid of the stuff, then fill up with clean air, then compress that clean air, kaboom, power stroke, right? Here we go. Hot side of the fridge, right? That's where the compression is happening. That's the high pressure side, right? Compressors, talked about that, and then we've got the fire plunger. You guys ready for the fire plunger? Every year, you know, when we start this unit, I'm like, the fire plunger is in this unit. Okay? I just get really excited about this thing. How does this work? Oh, I know, that's to prevent like cataclysmic explosions or something. It's got like a safety thing on there. How important is safety? Okay. They say use a little bit of this tinder. I like to use cotton. Maybe that's bad though. So I'm going to use just the tiniest little wisp of cotton. This is my fuel. I'm not going to use diesel because I'm going to use cotton. And this thing's nice because I can just stuff that thing in the end there. Oops. It's gone. Go back in there. Don't laugh at me. Sometimes that makes it go in. Okay. Come on, dude. It's like my fingers are so dry that it's sticking to my fingers. Okay. Let's see if I can tease it in there. Yeah, yeah, yeah. Okay. Yeah, that's a stupid joke. Okay, here we go. So I've got a little bit of cotton there. I've got air. I'm going to press the plunger down really, really fast. Yeah? And I can only do this once, so don't like not pay attention. Okay? I'm going to press the plunger down really fast as the air molecules, can we see this on the camera? Hello? Yes, we can. Okay. As the air molecules bounce off the piston, they come off faster and faster, and the temperature should rise to the point where the cotton spontaneously will ignite. Are we ready for this?
Yeah.
Okay. 1, 2, 3. Fire, baby! Yeah! Thank you. Woo! Showing proficiency in PowerPoint and physics. Ooh, white screen. Ooh, black screen. B and W when you're showing a thing. Yeah. What is it? It's like there's some function you can hit that will tell you all the little keyboard shortcuts. All right. Oh, the next one, the Murray refrigerator. Okay, so let's escape from here. Let's go here. What are you, Firefox? Oh, there we go. Two temperatures. Temperature 1 is the temperature of the gas right when it comes. I know it's labeled 2, but it's really temperature 1. Temperature 1 is the gas right as it comes out of the bike pump. And temperature 2 is the second temperature.